Hi, so far so good, right? Okay, let's continue. Let's learn more about non-ohmic material, okay? So again, what is non-ohmic material? Basically, it will not obey the Ohm's law, where you got like the slope is this one is a linear one, which means it's not changing, and also mean like the resistance of that conductor is a constant, right? But here in this case, it should be something like this. We know like for the filament lamp, right, from frame, if you hit it for a while, you can see that, oh, it's really hot, right? And then you can see that later is we got the voltage keep increasing, the currents also keep increasing, but it increasing at a slower rate, right? We can see here at each point here, there will be one slope itself, right? Like at this point, when say this is the slope, or like at this point, this is the slope, and this point, this is the slope. So if you have learned about derivative, maybe some of you have done some advanced math like higher advanced math level, but if not, you can think simply like we got I over V, right? And then we got some change of I over some change of V, right? Then we got this one as the slope, right? But if this is a constant one, but here we can see that there was just like some little change here can be considered as a line, right? As a straight line. So that's why this change have to be just like little change, you know? Little change. It's a very little change. So then it will be like noted as a d. So di over dv will become the slope at a particular point here, and that's why it have the name instantaneous. Okay, you remember if you recall instantaneous. Oh, my bad, this is not very clear handwriting, right? Let me write again, sorry. Instantaneous. Okay. So if you remember about like in the topic A, we got something like v equals to dx over dt. So that's the same thing. Also, the instantaneous velocity is that a little change in the displacement over time. Okay. Yeah. So it's just a review. If you want, we can discuss more about this concept. Okay. So let's just get to the point here. We have to really care for just a little change when everything can be considered as a linear, you know, just a linear, a straight line. So then that will be like the change here will be 1 over r, right? That would be the slope here. So basically you can see that the slope keep changing, right? It become more shallow in the end, which means that the slope is being decreasing, right? It's less steep in the end. It's more shallow. So that's why the slope decreasing. And now here we see it's actually 1 over r. So if this one is decreasing, then it means r is increasing, right? Right, Ari? So we can see, oh, so r is not constant anymore. Very clearly, it's not a straight line anymore. It's like this. So it means that r is changing, and that's a non-ohmic. And we can also see that as v keep increasing, we can also see that, oh, my bad, that r keep increasing. Okay, so there should be some correlation here. So what's the reason behind this, and what is the nature of things going on here? Just have a look. And actually, like from the materials to make the filament lamp, it's actually a metal that it can provide free electron, right? We got like the free electron, it's like a swarm, right? It's swimming through, try to get through the narrow gap between the metal atoms in the that follow some crystallized structure, right, of the metal, and tries to swim through. So when we apply a voltage across a section of the Y. It's just like plus and minus here. It's like a signal, hey, come on, electron, let's go. Let's follow the force. Let's follow me. Something like that, you know. Just I remember that this one trying to push the current through. Okay. Okay, so by doing that, we can see that all the electron will flow through here and in some directions. That's why we got the electricity, right? We got the electric current. So when we got these molecules moving more, you know, it's vibrate more. So then it's not easy for the electron to get through anymore. It's harder. That's why that we said that there's a resistance increasing here. So does it actually like the statement here say that the temperature causing more atoms vibration? So does temperature is the cause? Is temperature the cause? The answer is no. Okay, temperature is not actually is not the cause. Why? Because temperature itself is just a measure, you know. And this is a good revision for topic B as well. Okay, just have a look at the topic B again. It measure what? It measure the average kinetic energies of all the particles of all the molecule in the substance, right? Yeah. So here, more vibrations, right? So it should be more kinetic energy, right? And if this is more kinetic energy, then it's just like high temperature. So actually here it's just temperature and average kinetic energy or like vibrations of the molecule. They are in correlation with each other. They just correlate with each other. It's not like temperature causing this one, okay? But actually this one is the thing that is it first. And then we just got the temperature measured. Sounds good. So be careful. Temperature, if it causes more vibration, then this is not a good statement. It's a wrong statement, okay? Be aware with that, because I think that you also need to answer some question in the paper number 2. So make sure that you don't write something like this, okay? Okay, so let's get back to this one. Here we see is the at higher temperature, the resistance increasing. Okay, it makes sense, right? So that's why we got it like as temperature increasing, we got this one increasing as well. That's why the slope here is a positive value, and that's why we call these materials is a positive temperature coefficient positive, right? So this is called like PTC, okay? Positive temperature coefficient, okay? And it will be designed as a thermistor. It means that it's a resistor that depends on temperature. And we actually do have some other resistor that actually negative temperature coefficient, negative. So it means that the slope is a negative one, alpha is a negative one, and as the temperature increasing, the resistance actually decreasing. Oh, sounds weird, right? So how come? How come something like this happen? And actually, this is kind of out of the scope of your IBSL level, but I would love to also explain it to you, and it's not that very difficult to understand. So if you want, go ahead and then you can watch the next video, the last one, number 3. But I think that so far we're pretty good with the concepts here, right? Like for some positive thermistor, you can see that as temperature increasing, it's also like increasing, right? And it's pretty like a linear one, right? But you can see it, there's also like, oh, some little curve here, right? Some little curve here. And it's very interesting, like you can see as temperature increasing, it's actually decreasing. And like even for this one is more clearly like that. It's also like decreasing the resistance, right? As temperature increasing. So why? Okay, stay tuned with me for the next video to figure out about that. y. Okay, thank you. Good luck.